Sometimes it's helpful to take a large matrix and partition it into smaller submatrices, either vertically or horizontally or both. So that's what we're going to talk about today, is partition matrices. Now, let's just have a matrix that we call U. Not me, but U. And let's have it be a 6 by 5, which is a pretty large matrix, especially by hand. So let's give it the values going across: 3, 5, 6, 4, 2, 1, 2, 5, 3, 2, 4, 9, 11, 8, 2, 7, 1, 8, 4, 3, and on the last row, 4, 16, 9, 6, 3. So as you can see, that's a pretty large matrix that we can actually partition. So let's say we want to cut U into 4 pieces. No, I'm just kidding. The better way to say that, I guess, would be to partition the matrix U into 4 sub-matrices. So we're going to have U1 be a 3 by 3 matrix. We're going to have U2 be a musical group, or a 2 by 2 matrix. We're going to have U3 be a 2 by 3 matrix, and U4, excuse me, be a 3 by 2 matrix. So U1, we're going to take this first section. If you notice, we break that up and we have a 3 by 3. So I'm going to write this in blue. U1 is 3, 5, 6, 1, 2, 5, 4, 9, 11. I don't know if you can tell that's blue, but it is. Okay, then U2 is a 2 by 2 matrix, and hopefully you can see this in green. We're going to take this section here. 4, 2, 3, 2. Can you see that? Okay, good. And the next one we're going to do in red. U3 is a 2 by 3 matrix. Where can we find that? Right here. So 7, 1, 8, 4, 16, 9, and the last one will be in black, and it's what's left over, the 3 by 2. So we have 8, 2, 4, 3, 6, 3. So we just partitioned U into 4 submatrices. This can be helpful when a horizontally adjoined matrix with 2 submatrices is pre-multiplied by its transpose, which is a vertically adjoined matrix with 2 submatrices, and that results in a large matrix containing 4 natural submatrices corresponding to the product of each combination of the original 2 matrices. I hope you got all that, because I'm not going to do a demonstration. Just kidding, I am. So let's go back to our CD matrix that we did in the previous video on adjoined matrices. So let's say we have an adjoined CD matrix, and we're going to take the transpose of that and multiply it by itself. Okay. So this is going to equal 2, 0, 6, 7, 5, 3, 4, 1, 8. This is, if you recall, the C matrix that we used in the previous video. And we're going to separate it 2, 6, 1, 3, 4, 7, 3, 0, 2, and I didn't make this long enough, I'm sorry. 2, 5, 1, and this was our D matrix. So that's the transpose of our CD, and we're multiplying it by our adjoined CD matrix, going across 2, 7, 1, or excuse me, 2, 7, 4, separated, 2, 3, 3, 2, 0, 5, 1, 6, 4, 0, 5, and then we have 6, 3, 8, 1, 7, 2, 1, our original CD matrix. And let's just call this B to be short. So B is going to be equal to what? Well, we know that the transpose of the CD matrix is a 7 by 3 matrix, and this is a 3 by 7. So the resultant matrix is going to give us a 7 by 7. So it's going to be quite large. And when you do this matrix multiplication, the values that you get, 40, 32, 56, going across, 10, 48, 18, 10, 32, 83, 57, 47, 62, 27, 42, 56, 57, 81, 22, 72, that's 28 and 21, 10, 47, 22, 41, 37, 8, 35, 48, 62, 72, 37, 74, 23, 33. I'm saying these out loud so you know what I'm writing. 18, 27, 28. We have 8, 23, 13, 8. And then the last row, 10, 42, 21, 35, 33, 8, and 30. Wow, that's large. So like I stated before, we have here the CD matrix, a horizontally adjoined matrix with two submatrices, and it's pre-multiplied by its transpose, which is a vertically adjoined matrix with two submatrices. So it results in a large matrix, and this actually contains 4 natural submatrices, which correspond to the product of each combination of the original 2 matrices. And I'll try to highlight this for you. I didn't divide this, but I'll do that for you now. So when we do matrix multiplication, essentially we're taking our C matrix here, that's blue, and multiplying it by C matrix here. Sorry, I covered the 6. Okay, so this is a 3 by 3, and this is a 3 by 3, so it's going to give us a 3 by 3, which is actually right here. And we're going to call that B1. B1 is a 3 by 3, and it equals 40, 32, 56, 32, 83, 57, 56, 57, 81. And this is actually multiplying C by C. That's what you get. So I'll do the next one in green, is B2. B2 is going to be a 3 by 4 matrix. Sorry, you can't see the green too well. And B2 is actually going to be This one again, remember when we do matrix multiplication, this could be that one times this one, which is C times D, which results in this one. Ten, 48, 18, 10, 47, 62, 27, 42, 22, 72, 28, and 21. Our 3x4 matrix. And once again, forgive me, you can't see that too well. Okay, our next one, I'm going to do in red. You get by taking this one here and multiplying it. If you remember how to do matrix multiplication, you're going to do it by this one. Sorry, I meant to say that this is C times D matrix. So the result for the one I've highlighted in red is going to give you, this is a 4 by 3 times a 3 by 3 gives you a 4 by 3, which is this one. So we can call that one B3, the 4 by 3 matrix. Ten, 47, 22, 48, 62, 72, 18, 27, 28, 10, 42, and 21. The last one, oh, sorry, that is, see if you can see that here. That is, what is this? It's D times C. DC. Okay, last one I'll do in black. And as you can guess, it's going to result in this portion here. And it is taking this bottom one, which is D, times this one to the right, which is also D. We're going to call that B4, which gives us a 4 by 4 matrix. 41, 37, 8, 35, 37, 74, 23, 33, 8, 23, 13, 8, 35, 33, 8, and 30. Which, so you can see this is actually D times D. It's in 2D. So as you can see, the resultant matrix is quite large. It contains 4 natural submatrices that correspond to the product of each combination of the original 2 matrices. The original 2 matrices being C and D. So taking the product of each combination. So we have C times C, C times D, D times C, and D times D. So I will show you this on Excel. It's much easier and doesn't hurt your hand as much to write it out. Voila. Okay, so let's start by taking the transpose of the CD, which once again, this is the joined CD matrix. You just take by copying and pasting C and D into here. So we're going to copy this one and do a special paste. Transpose paste. And let's add the line here. You just go to right click and go to Format Cells. Click Border. It's going to be a horizontal line to separate those two. Alright, now we're going to get B, which is the matrix multiplication of the transpose, comma, adjoin CD matrix, Control Shift Return, and we get all our values there. I'm going to first do B1, B2, B3, and B4, and then I'm going to separate these. so that we can easily see the four natural submatrices that come about. So as we talked about before, B1 is equal to C times C. So it's going to be matrix multiplication, C, comma, C. So I'm sorry, it's supposed to be since we're doing the transpose of CD times our joined CD matrix, is actually going to be, sorry for that, the transpose there, comma, a regular C, Control-Shift-Return, and those are the values that we get right here. Now B2 is going to be our transpose of C times our natural D, and those are the values that we find here. Then B3 is going to be our transpose of D here, comma, our natural C, which we find here, and B4 is going to be our transpose of D, comma, D, which we find right here. So let's separate all these. We are going to need a line here to separate the submatrices, and then a line here. And there you go. You can see it's now partitioned into four submatrices there. Once again, it's a large matrix when we take the horizontally adjoined matrix, our CD here, with two submatrices and pre-multiply it by its transpose, which is a vertically adjoined matrix with two submatrices. We get a large matrix that contains four natural submatrices that correspond to the product of each of the combinations of the original two matrices. So C times C, or pretty much the transpose of C times C, then C times D, or the transpose of C times D, then transpose of D times C, transpose of D times D. So let's compare that to what we have over here. We do get the same result as we did right here, and our B's are the same. This is C transpose times C, B2 is C transpose times D, B3 is D transpose times C, and B4 is D and D, D transpose D. And there you go. That's some useful knowledge about partitioned matrices and how they can be helpful. Hope you have a good day.